everyone. My name is Márton Braun. I work as a developer relations engineer at Google. And this is Composing an API with Kotlin, Volume 2. In this talk, we're going to take a look at some of Jetpack Compose's APIs and learn about interesting ways of using Kotlin features to achieve APIs, looking at both the APIs themselves and also a bit of the implementations in the process. Now, you don't need to know Android or Jetpack Compose to understand this talk. It's kind of a general Kotlin topic. And we're also not going to learn Compose during this talk. It's really just to inspire you to use Kotlin in interesting ways. This is Volume 2, because I've already given a talk with the same title at Kotlin Dev Day back in May. And I encourage you to grab this link and check out this talk later on. But we're going to cover a different set of APIs and Kotlin language features in this iteration of the talk. All right, in case you're not familiar with it yet, what is Jetpack Compose? Let's start from the beginning. Compose is Android's modern toolkit for building native UI. It's replacing the view system that we've had around for more than a decade. And most importantly, Compose is entirely Kotlin. So it's powered by a Kotlin compiler plugin, and all of its APIs and implementation are built in Kotlin. Quick disclaimer here, some of the code that I'm going to be showing you is going to be simplified so that it fits on the slides and so that we can focus on a single feature at a time. But you should and you can very much check out all of the implementation of Compose yourself as well. So because Compose is open source, you can browse its code if you want on the web, for example, by going to cs.android.com. Or you can do the same thing within your IDE by opening a new Compose project in Android Studio and then navigating into the declarations with all of the tooling of the IDE available for you. This is my preferred way of exploring Compose code, and it's how I prepared most of this talk as well. All right, so let's start going through the features now, and we're going to start from the simpler ones and then move on progressively to some of the more complicated things. So in the previous iteration of this talk, I already covered default arguments, and I've shown this example, which is a function that creates a rounded corner shape. It has parameters to customize the rounding amount on each of its 4 corners. And all of these are defaulted to 0 DPs, DPs being a measurement unit on Android. It stands for density independent pixels. And we can already see a cool use of a Kotlin feature here, which is this extension property that's defined on numerical types that allows us to write down something like 0.dp and create a typed measurement value. The call site of this function looks something like this. Because we have default arguments for everything, we can specify just the rounding that we need. So for example, we can round just the top end corner of this shape if we want to. Or we can add more parameters and get more rounding, and everything that we don't specify at the call site is going to default to 0. And that's a small example of default arguments in Compose, but I really want to stress that default arguments are used very heavily in Compose. So here's, for example, the text function, which you use to show text on the screen. And as you can see, this has an overwhelming amount of parameters. But the only required parameter is this string at the top, and everything else is optional. So that means that you can already create a piece of text by just passing in a string to this function, and that would already display on the screen. But then you can go in and keep adding more parameters to customize how that text looks. So for example, I could also provide the font size to make this a bit smaller. I could add a weight to make it bold. I could add a modifier to limit the width of the text that's being displayed. That would now break it into multiple lines. I could limit the number of lines that the text can have. And if I don't like this behavior, which is that anything overflowing is clipped off by default, I can also specify that parameter and ellipsize anything that doesn't fit within the constraints here. And it's not only default arguments that make all of this flexibility possible in Compose, but also named arguments. So on one hand, named arguments let us have a nice readable call site because we see exactly what the values that we're passing in are. But they also allow us to pick off any of the values from the parameter list, anywhere in the parameter list, instead of having to go in order from the top of the parameter list, specifying everything until we reach the parameter that we actually want to customize. And the same pattern can be found in other basic composables as well. Here's, for example, the button composable. Again, a lot of parameters, a lot of default values. but only a few required ones. So if we take a better look, we'll see that there's only 2 required parameters to a button. And this actually brings us to something else that's used very heavily in Compose, which is function types. Now, if you're writing Kotlin, you're likely used to using a lot of function types. And especially if you're using Compose, you have been using a lot of functions and lambdas all over the place. But I really want to emphasize that this is something that enables Compose's APIs to work. Let's take a look at the call site of a button, which specifies just these 2 parameters, and see how these are used. So for the first parameter, the onClick parameter, this is essentially a callback, which the button is going to call whenever the user taps it. Here we are creating a lambda that we're passing into the button function, and we are specifying the name of the argument so that we have, again, a readable call site. The other parameter is a lot more exciting. This also has a function type, but it's also marked composable. So with this parameter, we're passing in a piece of UI to the button composable, because button can render a button for us, which is like a colored rectangle, which has click handling and has ripple effects when it's tapped and so on. But we do have to show something on the button, whether it's an icon, a piece of text, an image, whatever you can imagine should be on a button. And so button receives whatever it should display on the button as a parameter, as a function type. And by convention, when we pass in UI to another composable function as a parameter like this, the convention is to call this parameter content and place it at the very end of the parameter list, which allows us to use this trailing lambda syntax in Kotlin, which is to pass in the braces outside of the parameter list of the function call. And thanks to this, anything that we pass in as the contents of the button is visually nested within the button. So for example, in this case, I'm passing in an icon, which is then shown on the button, something like this. And we have this really nice visual nesting where we can see that the icon is inside the button on the code level. And again, we could pass in something else here. So for example, if I wanted to show a piece of text on the button, all I would have to do is pass in a function that calls into the text function there. OK, going further with functions, I want to show you a quick example of one of our Compose sample apps called JetSnack. In JetSnack, we have this screen, which is the details of a specific snack. And I want to focus on the title that's being shown at the top of the screen here. So that title, which says chips and the price of the item, that needs to be synchronized to the view that's below it, which is being scrolled up and down in this video here. And it also needs to be sticky when the view is overscrolled. So based on the scrolling state of the view below it, we have to move this title around as the screen is being used. Here is the code that powers that title, a simplified version of it. So first of all, this takes a snack as a parameter, and it creates a couple different pieces of text, which are going to be the name, some other information, the price, and so on. And all of this happens within a column, which is a layout in Compose that arranges its contents vertically under one another. So that's how we display the information. Let's take a look at how we move this around to account for scroll state. So we take a parameter here, which is an int value for how much the other view has been scrolled so far. Then we use this variable to calculate the offset that our title needs to have. And finally, we apply that offset to all of the content that the title function is creating by using the graphics layer modifier. Now, the way that Compose works is that there are pieces of state within your application that Compose is keeping track of. And this scroll state that we're passing in at the call site is one of these composable pieces of state. And so whenever that state changes, Compose will detect the change in the state, and it will know where that state has been accessed, and re-execute the code so that the UI can be updated to match the new state. In this case, that means that the call site of the title function here, where we are reading the value of the scroll state, is going to be re-executed every time that the scroll value changes, which happens several times a second as the user is continuously scrolling. So that means that everything around the call to the title function and the call to the title function itself would be re-executed, recreating all of the UI and then offsetting it to a new place, which is a lot of work, and we want to avoid that. So to fix this, what we need to do is instead of reading the value of this scroll state before the title function is called, we want to read the value of that scroll state after the title function is called. But we still do need that value somehow. And again, function types can come to the rescue here, because instead of passing in a specific value, we can be lazier. We can defer the read to that state and just wrap it into a function at the call site, which can then be invoked later on within title. Now, we are still calling this function here in the body of the title function, so Compose would see that whenever the scroll value changes, it has to re-execute all of the title function, again creating all the pieces of text from scratch, which is too much work to do. But luckily, we can do even better. We can defer this read even later on by not passing in a specific value into the graphics layer modifier either, but instead using an overload which takes a lambda as a parameter. Graphics layer will be triggered at a late stage of the rendering pipeline in Compose and apply the changes that we packaged into the lambda that we passed to it. So if we move all of our calculation of the offset and the read to the scroll value there, then Compose will no longer need to invalidate our entire title function here, but only the application of the graphics layer modifier. So this way, all of the UI we've created can continue existing, and only the offset is reapplied as the scroll state changes. Now, I was a bit hand-wavy with the explanations here, because this would be an entire talk on its own about Compose state management. But we have a great article about this that you can check out after the talk. The link to this is going to be in the resources at the end. I also do want to mention that this kind of pattern of deferring work by using functions instead of values, so functions that can produce the required value instead of the actual value, is also present in the standard library in many places. So, for example, all of these functions take other functions as parameters because the values that those functions produce are only needed in certain scenarios. And if we don't run into that case, we don't want to do the work of producing these values. Again, I encourage you to take a look at the implementation of all of this, this time in the standard library. All right, let's keep moving. Next up, I want to talk about delegates, which are one of my favorite Kotlin features. And first, we're going to recap what delegates are by looking at one of the built-in ones in the standard library, and then we'll see how how Compose can use delegates. So in the standard library, we have this lazy delegate as an example. And here I'm using that to create a property that stores the value of pi. And I have a main function which reads the value of this property twice as it's executing. And thanks to this being wrapped into a lazy property, the value will only be computed when I first access it, which is on the first line of the main function. And after we do that expensive calculation, the value will be cached, so any subsequent reads of the property will just reuse the existing cached value. In practice, this means that whenever I run this main function, it will take a while to output anything, but then everything is output basically at the same time, because the calculation will only hang the first print statement here, and then again we get the cached value from the lazy delegate. Now, how this works behind the scenes is that whatever you place on the right-hand side of the by keyword, whatever object is being returned by lazy here, has to have a getValue function. And whenever the property is read, that getValue function is what will be invoked to produce a value. And similarly, if we weren't doing a read-only property, but a var instead, then we could also have a setValue function, which would have a very similar signature. And one last important thing about delegates that's especially important for Compose is that you cannot just delegate properties which can live in classes or at the file level, but you can also delegate local variables. So I could move this into a local variable and still use delegation with it. And this comes up a lot in Compose because a lot of our Compose code resides just in the body of functions. So being able to use delegation within a function body is very useful for Compose. So how are delegates used in Compose then? Here's an example of a name input field. We're creating a piece of composable state here, which is going to store the name. And then we're using the outline text field function to give the user a field where the current value is displayed. And they can also type on the keyboard to edit the value. That piece of composable state is being created with these function calls, which we're not going to detail now. Just take my word for it that this creates a mutable state of string object. And then to link this to the text field, we first need to pass in the current value, which we do by reading the value property of the state. And we need to pass in a function that the text field can invoke so that it updates the value that's stored in the mutable state, essentially synchronizing as the user is typing new values. But instead of assigning the state to a local variable, we can also choose to delegate a local variable to this state. And in this case, the type of this variable would no longer be a mutable state of string, but just the contain type, so string itself. And that means that we no longer have to use the value property on name every time we want to read or write it. Instead, we can just read or write this local variable with simpler syntax. And those reads or writes will be delegated to reads and writes of the mutable state that's backing it. If we take a look at the declaration of mutable state to go looking for these get value, set value implementations, we'll first of all find that mutable state has a read-only interface above it as a super type. This is very similar to how the standard libraries collection interfaces are structured, where there's a read-only list, for example, and then there's a mutable list variant of it. Among other things, this enables that type parameter in the read-only interface to be covariant, which I think is a really nice addition of pulling out read-only interfaces like this. And we're not going to go into what that means, because it takes, again, another talk to discuss Kotlin generics in that detail, but I'm very happy to chat about it later. OK, so we have these two interfaces. A read-only one, which declares value as a read-only property, and then the mutable one, which overrides this and changes it into a var, essentially adding a setter, which is also a neat pattern that you can use. But where are the get value and set value functions that we've been looking for? Well, those are not part of these interfaces. Instead, they are created as extensions on the interfaces. So if you have a regular state, you have the get value extension function available on it as an operator, and that means that you can delegate a read-only variable into a state. But if you have a mutable state, you also have the set value extension, and in that case, you can delegate a var into a mutable state as well. Here, the important idea is that delegation support doesn't have to be part of the type to begin with. You can have existing types and add delegation support after the fact by just creating these operators as extensions. And another nice bonus of using extensions here is that they can be inline functions. And there is this property parameter in both of the delegate functions signatures, which normally has to be allocated and passed into the get value and set value functions. This is a Kotlin reflection type, which describes the property that's being delegated to our current object. But because these are created as extensions and they are inlined, the compiler will see that neither of them actually use the value of this parameter, which means that we can spare the allocation of these k-property instances. This is kind of a small optimization here, but as this is part of a framework, performance counts more than in application-level code. Also, this pattern of adding on delegation to existing types is also present in the Kotlin standard library. For example, you can delegate a variable into a map instance, and then reading and writing the value of that variable will actually read and write values inside the map using the name of the variable as the key for all of those accesses. And this also has a very interesting implementation that we don't have time to discuss, so I'm going to leave that for you to do later on. All right, next up, we're done with delegates, so let's discuss destructuring declarations now. So destructuring is a feature when you can take an object in Kotlin and create multiple variables, destructuring your initial object into those newly created variables with the syntax that you can see here. This color object is an example of destructuring supporting Compose, where you can take your color and destructure it into the individual color channels, so red, green, blue, and alpha values. If we take a look at the declaration of color, we'll see that it's actually an inline class, and it wraps a single unsigned long value, which is very nice for performance, because at runtime, any color object that you create is only going to be a primitive value, which is very performant. But the great thing about inline classes is that they are still classes, which means that they can still have functions and properties inside them, as long as you don't need to store any additional values other than that single one that you are wrapping. So in the case of color, for example, there are computed properties for red, green, blue, and alpha values, which all have custom logic in their getters that take that single stored value and then use some bit-level operations to shift things around and extract the individual color channel values from them. And then to support the destructuring that we are looking at, we also have all of these component operators inside color, which are simply reading the values of the properties declared above them. So these are what are going to be invoked to initialize those 4 values that you can see on the call side on the very first line. The important idea in this example is that your component functions, when you create destructuring support for something, don't have to return existing values, like it happens for data classes, for example. They don't have to return values that are already stored within the class. They are just functions, so you can place arbitrary code inside them. In this case, we are running all of the code in the getters of these properties when the component functions are called, but you could really do arbitrary things there. If you really wanted to, you could be making network calls in there. Probably shouldn't, but you could. Destructuring can also be used with state management. So we've just looked at how we can delegate a variable into a piece of state and get nicer syntax with that. But there's also an alternative option if you prefer the syntax of that, which is to destructure a piece of state into 2 variables. In this case, the first variable that you destructure into is going to be the current value of the state. And the second variable is going to be a function type which acts as a setter for that state. So whenever that function is called, the incoming value of it, the parameter passed to it, will be the new value of the state. And this can be up to your personal preference if you want to use this syntax versus the delegation support, but it can also be a nice fit with other Compose APIs. For example, for using this text field here, we were previously creating a new function that can just set the value of name to whatever the incoming parameter of that function was. But now we can simply pass in the setName function itself, because essentially what was required from us is just a setter for the state. For the implementation, these component functions that are required for this are part of the mutable state interface. So there's a component1 function which just returns the value of the property above it. And then there's a component2 function which creates a new function that is able to set the value of the property. What's interesting here is that you usually think of destructuring as destructuring an object into some kind of values, some kind of data. But you can also destructure into arbitrary types, for example, into function types if you want to, and if you can find the use case for it. Okay, one more example of destructuring, and then we're done with this language feature. I want to show you an example of using constraint layout in Compose. And constraint layout allows you to create references, assign those references to all of the composables that are nested within the constraint layout, and then use these to set up constraints and position things relative to each other. Let's see how that actually looks like in practice to better understand it. So here, for example, we are creating 2 references, which we're calling button and text. We're assigning these to 2 pieces of UI that are nested within the layout. There's a button and a text, which receive these respective references. And then we are linking these together by saying that the top of the text should be linked to the bottom of the button, and there should be a bit of margin in between them. So something like you can see on the illustration here. An interesting bit of information here is that all of these APIs that we're using, so the create_refs function call and the constraint_as modifiers, all of these are contained by scopes in Compose. So for example, the function that we're passing into constraint layout has a receiver which has the type constraint layout scope, and that's where that create_refs function is coming from. That means that create_refs cannot be called outside of this scope that the lambda passed to constraint layout creates. Okay, let's focus in on the destructuring now. So we were calling this create_refs function, and we destructured it into 2 references. How does this work? If we look at the types, we'll see that on the left-hand side, we have 2 objects which both have the type constraint layout reference. And on the right, we have a constraint layout references object. Now, going to the implementation, create_refs isn't really doing much work. It's just returning a property that's stored right next to it. But if we take a look at what the type constraint layout references is doing, that's a lot more interesting. So this type doesn't really have any specific components. In fact, it can be destructured basically any number of times, well, up to 16 times, but that's probably enough references to create at one time. And then every time that it's destructured, it just keeps calling the create_ref function to dynamically create new reference objects, while incrementing some kind of internal counter for generating the IDs of these. So what's really interesting about this example is that the components aren't destructuring into some known objects ahead of time. Instead, as the destructuring happens and the component functions are called, they keep allocating new objects every time. And also, this constrained layout references object exists solely to support destructuring. It doesn't have any other APIs. When you call create refs and you get this object, you can't do anything with it other than to destructure it. Okay. Moving on, I wanted to show you an example of strongly typed APIs in Compose. There are a lot of examples of this. Basically, almost everything in Compose is nice and strongly typed thanks to the powers of Kotlin. For example, if you look at measurement units like SPs and DPs in Compose, all of those have really nice typing instead of using something like primitives in their place. But what I chose as an example to look at strongly typed APIs is this one. So we're going to take a look at a few basic layouts in Compose and positioning items within those layouts. So here are these three basic layouts in a box. The various components that you place in there are stacked on top of each other by default. In a column, the items are stacked vertically under one another, and in a row, the same thing happens, but horizontally. So we're going to take a look at two of these. We're going to take a look at a box and a column. And in both of them, we're going to place just a single piece of text. What I want to show you here is that within these layouts, we have the ability to align the contents. In the case of a box with a piece of text placed into it, we can use the align modifier to align it both vertically and horizontally within the box. So for example, we can align it to the bottom start like this. And other options would be things like top center or center end. You can imagine that there's 9 different options of aligning something within a box. In contrast to this, if we are using a column and we've placed a text within that, because other pieces of UI that we nest in the same column would be stacked vertically, we can only do horizontal alignment of this piece of text. So in this case, I've chosen to center it horizontally, and our only other options would be to align to the start or to the end of the column. What's an interesting thing about this API here is that in both of these cases, we're using the same align modifier to do this alignment. And the values that we're using to specify where we want to place our UI both come from the alignment type. But we have different sets of values available in these two cases, because in a box, we're doing two-dimensional alignment, whereas in the case of a column, we're doing it on just one axis. So how does this work? Well, both of the lambdas that the layouts take as parameters have their own scope types, and the align functions that we're using in each case are actually part of those scopes. So these are different align functions that come from those receivers, and they have different parameter types. In one case, we have the regular alignment type inside the box, whereas within a column, we have a more specific horizontal alignment parameter. This still doesn't explain where the different values come from, which are both accessed from the alignment type, though. But it does mean that if we were to, for example, switch up these values, then these would not be compatible anymore. So we cannot do a one-dimensional alignment inside the box, because that doesn't make sense. And we cannot align something to the bottom start of a column either, because again, these are mismatching types. So let's see how we can implement something like this. First of all, going to alignment, you might have expected this type to be an enum or something like that, maybe a sealed class. But it actually turns out to be a functional interface, which is another fun feature of Kotlin. And there are also some other more specific nested interfaces, horizontal and vertical, inside it. As for where those values come from, things like alignment.topStart, for example, those are declared as properties inside the companion object of the type. So accessing these will look the same as if you were accessing something like a set of enum values, so like alignment.center. But they are actually properties that are declared in the companion object, which means that we can also freely choose the types for them. So while all of these 2D alignments are defined here, and they have the 2D alignment type, we also have the one-dimensional alignments defined in the same place with the same syntax. But these are typed with the more concrete types. So the first set of these are horizontal, and then the second set are the vertical alignments. You can also note that to match the syntax that an enum would have, for example, we are breaking the property naming conventions that we usually have in Kotlin. So all of these properties that are in the companion object actually start with uppercase letters. So this is a pattern that is used a lot in Compose. You can find this in a lot of different places. And you can also apply this in your own code to make something that looks like an enum, but is actually backed by arbitrary implementation. Oh, and it's also not exhaustive, because we're just defining properties, and we can have an arbitrary set of these here. All right, that's everything that I wanted to cover in this talk. Here are some resources that I encourage you to have a look at. So first of all, there is the first iteration of this talk, which covers a different set of Compose APIs and language features from Kotlin. Then there's the article I mentioned about debugging recomposition, which goes into more details about how Compose is rendering UI and how you can avoid re-rendering too much of your UI at a time. And then one more link, the third link I want to highlight, is that you can always browse the sources of Compose on the web if you want to. I'm going to let everyone take a picture of that. And with that, thank you for attending this talk.